Okay, let's just have a look at the parametric form of the hyperbola. I've just drawn in one branch of the hyperbola. Okay, so there's a random point on it, x, y. Now to get the parametrics for this one, again I draw in the auxiliary circle, which of course when we talk about the hyperbola, we don't have a major axis and a minor axis, we just have the one axis, that being going out to the actual vertex of the hyperbola. So it would be x squared plus y squared equals a squared. Now how do we create the angle? Well, similar to what we did with the ellipse, you remember we dropped a vertical, but here when we drop the vertical, we do something a little bit different. From the x-intercept, we draw in a tangent. And of course we know the tangent will meet the radius at right angles, and thus we now can create an angle at the centre of theta. All right, well, x then would become the hypotenuse of that triangle. And so x over a will be the secant of theta. So x is a sec theta. So that's how we can get the x coordinate. Of course, getting the y coordinate's a little bit more difficult. With the ellipse, we could draw in a second circle with regards to the other axis. We don't have that with a hyperbola. So I guess the easiest way of doing it is we know what the equation of the hyperbola is. We can sub it in and then from there work out what the other parameter needs to be to make it work. So if I sub in a sec theta in for x, and rearrange that and make y the subject, using some trig identities, we end up with b tan theta for the parametric on the y value. Okay, so there are our parametrics for the hyperbola. A sec theta and b tan theta. It turns out, I mean, we could go through and derive these all again, but they turn out to be very similar things to what we saw with the ellipse. Once again, you'll notice the similarity with the tangent and the actual conic itself. You see that same pattern, but this time it's a minus in between. You've got the x1 on a squared minus y1 on b squared, which matches up with the formula nicely, x squared on a squared minus y squared on b squared. So you should find a similar thing happening there with the tangent. And with the normal, you end up, you remember it was a squared minus b squared with the ellipse? Well, with the hyperbola, the normal turns out to be a squared plus b squared, but again, that could be written as a squared e squared. So both the ellipse and the hyperbola, the normal will equal a squared e squared. Here it's a plus. You'll remember with the ellipse it was a minus with the normal. In parametric form, we'll end up with x sec theta on a minus y tan theta on b. Again, very similar to what we saw with the ellipse. And the normal would turn out to be ax on sec theta. So again, you'll see the sec theta moves to the bottom and the a moves to the top, and same sort of pattern that we saw. When you're differentiating these, we didn't actually talk about these when we were differentiating trig. If you want to differentiate sec, you will get sec tan. Okay? You can prove that very easily by changing sec to be 1 over cos, then use your quotient rule and so on. So it turns out to be sec tan. And of course tan we did do before. That one turns out to be sec squared. Okay, as I say, I won't do any more examples because it really is the same as ideas and things as the ellipse. Slightly different equations we end up with. So a couple more out of 6C from Patel. And Unit 2 in our comma... Oh, the N has changed to an M, you'll notice. For this one. What is his name? Yeah.